And well, the first sessions are really, so we'll cover today basic theory of sister algebras and maybe a bit more, but probably not much more. So probably some of you already know about these things. And well, if you don't, some more of the detail, many of the details will be like on a sketchy basis. Right, so I'll start with a definition. Also, if you cannot read my writing, please say so. Right. So we'll start by saying what is a complex star algebra. So that is a ring A, which is also a complex vector space with a map. Like this with a star, that's called the involution. Of A that sends an element A to its star, and it satisfies under properties. The first one is that it's additive. The second one is that is convoluted, and it's anti-multiplicative. And idempotent. So it takes star is A. Right? And what are the easy examples of these things? And these are examples that we will have in mind. So the complex numbers, the star given by conjugation, and there's some question in the chat. Do I include a unit in my ring? Yeah, well, in general, I shouldn't be including a unit, but for many of the things, I will be just leaving the unit world, unless, so the unitizations and stuff like this will be not considered very formally. So when I need a unit, I will include a unit. So if we have time, we'll go into this. In principle, we don't need to do it. Other examples would be, of course, and so matrices over the complex numbers with the evolution of a matrix is just conjugate matrix. Okay, now I want to go from here to the definition of what a sister algebra would be. And for this, we need to talk about, want to give first the canonical example. So we take H, the complex Hilbert space. And we consider H set of linear bounded operators on this Hilbert space. So bounded is the same as continuous, and this is the same as saying, so the bounded or continuous, I just recall this. So means that so I'm as a constant, so there exists a constant such that C positive, so T bounded, there exists a constant positive such that this happens for every x. Yeah. And one defines a norm as the supreme over those vectors of unit of norm one, such that here the image of x. Okay. So this we approach with usual addition, so pointwise addition and composition. And also the identity, in this case, we have a unit. So is a complex algebra. It is non-commutative unless H is like the complex numbers. And it's also a star algebra. So that's a fact that one has from functional analysis. So given which we don't prove, a bounded operator. So the X is unique. It's star. Such that for every couple of vectors, it's y in H, one has Tx. Y is the same as where this thing here is the input of H. Okay. And now we come to the proposition that I mean, I won't prove the whole thing, but maybe two of the details that justifies the definition that we're going to give later. So that leaves me a little bit space. And let's take S and T, two operators. So then we have the following. So the first one is that the norm of ST, that means this product is a composition. So this is less than or equal to the norm of S. This norm of T. Second is that the norm of S star equals to the norm of S. Third condition, the norm of S is the norm of S squared. And the third condition is that one, so the identity plus S of S, it's always invariant. Okay, so and now let's do a sketch for so I just want to mention how one does 2 and 3. Because that motivates the definition of a sister algebra, which is what we're going to give later on. So for 2, so we take X in H with 1, and we compute the norm of S applied to X. That by definition, the square of this is by definition S of X product with itself, which is by using what the adjoint satisfies. So I can move this past to the left by adding a star, and this by Cauchy-Schwarz. Is less than or equal to this product. This, which at the same time is less than or equal to the norm of S star S minus the norm of X squared, and since X had norm 1, this is really this thing. So this implies that the norm of S is less than or equal to the norm of S squared is less than or equal to the norm of S sub S. Because the norm is the smallest C. I mean, it's this thing, it's the supreme of this thing, and it's the smallest C that this thing is satisfied. So this is where we get this inequality. Okay. Also, we can go now from 1. So I don't prove 1, but we believe it's true. So this is less than or equal to the norm of S star times the norm of S. And from here, we obtain that the norm of S is less than or equal to the norm of S star. And by symmetry, we get the other inequality. And so that's part 2. Okay. Now part 3. Yeah. Part 3. We also go. Now we use what we have proved already. So S squared is equal to this. This we already proved before. This is less than equal again. There is no, and this is less. This is actually equal because we know that this is the same. This is the same as this squared. So this implies that the number is S, the number of S squared. Okay, so that's the argument for that. So that motivates the definition of system algebra. And for this, well, I have to define like 2 concepts. First, what is a complex algebra? It's algebra to the norm. We denote as usual, such that this norm is somewhat negative. Elements, and also A together with its norm is limit. So these sequences have limits. Okay. And a sister algebra, that's the main object of the course, together with abstract concepts, of course, that is a complex algebra with an involution, in the sense that we defined in the beginning. Star, so we'll denote this by star, such that it satisfies this equation. So A star A, the norm of this is the same as the norm of A squared for every A in A. And that's an important requirement, which makes sister algebras rigid in some sense. And that has a name, it's called the C-star equation. And the origin of this comes from the Hilbert spaces. So what are the main examples? Well, we have already seen some, but example. First one is, of course, the average for a Hilbert space. So that includes C and it includes the math of C. If we take for the Hilbert space like C to the n, this form. And with n equals 1, this gives us exactly C, right? The second example would be, well, so if you take, that will be important later in the sense that it's a theorem, but not in the sense that we will prove it. So every starts with algebra of B of H, which is closed in the norm topology, which is really closed. So you take any subalgebra of such B of H, and which is closed under the involution and closed under the norm, this will become automatically a sister algebra because it satisfies the equation from here, from B of H. The third example, like if X is a compact Hausdorff space, then let C of X denote C of X comma C, and this is the same as the functions from X to C that are continuous. Right, so continuous complex valued functions from the compact Hausdorff space. That is an algebra with pointwise operations. It's commutative. It's algebra and is a sister algebra. Where we take the involution of f, x, is the same doing of x, and then complex conjugation, and the norm, which is super. Okay. Now, maybe going back to the comment that was made before, like whether we have units or not. This has a unit, of course, which is the unit function. Sometimes it's convenient not to have a unit. And I'll just mention this in passing. But if the space is not compact, but locally compact, we also have a sister algebra defined conveniently. So if X is locally compact, also, then one takes C0 of X, and this is a set of functions which are continuous also. And well, for epsilon, the set of the x's in X such that f of X is bigger than epsilon, this is compact. That's a condition. I was saying that f vanishes infinity. And the idea is like if you take, for example, C0 R, that would be like functions that something like this, right? So that would be kind of the idea. That is also a sister algebra with the same adjoint norm, but it's not necessarily unital. I mean, it's unital when X is compact. But it's not. It's unital. I know this in passing just in case. So other examples on constructions would be like if we take now a family. Algebras, then the product of these things, which is by definition is the set of elements in the set of strings, let me put it like this. But I want not to allow any strings, but the strings that have boundary. So that is also a system with pointwise operations. And the norm being the supremum of the norm. So one has to allow, I mean, it's not like just the set theoretic product, but the product in the category. I mean, if we have a finite number, and I want to emphasize this in particular, so if we have a finite number, then the product with the norm of the maximum is a system algebra, and in particular, so the emphasis of this is for some reason, you will see. If we take any product of finite matrices, that's also a system algebra, which is, of course, finite dimensional. Right? The finite dimensional thing. Okay, so we want to study a bit how which things appear in the general theory, and we will see that this is the standard model for commutative algebras, and this is the standard model for finite dimensional algebras. I don't plan to give details because that would take long, but I do plan to give some details. So for that, first, let me just define here, maybe that's the right point to do it. So now we have sort of the objects. How do we define the morphisms? That's another thing to do. So one first sets up the objects in the category one wants to study, and now we want to know how to compare them. So start from a morphism between system A and B. Is well a map that goes from A to B, such that is a ring homomorphism. Well, it's an algebra homomorphism, I should say. It's a complex algebra homomorphism. So it's additive, multiplicative, and C-linear, and it preserves the involution. Okay, so if A and B are unital, and then we also require that the unit of A typically will require this is mapped to the unit of B. So no mention here, and that's maybe the nice thing somehow, is that this is a completely algebraic thing. So we only require that the algebra structure is preserved and no mention to the continuity structure is given here. And this is because it will be automatic. So these things will be, so star homomorphisms will be automatically continuous of norm one. Okay, so we'll give some details coming up. And well, for this, we need to talk about a little bit of spectral theory. And of course, give some details, give some results. We take that for granted because they become tricky, but at least we get a flavor of how things go. Okay, so spectrum of an element. What is this? So I'll do this in the unital case now. Everything can be done in the non-unital case by adding a unit and things work out okay. But just to have a more streamlined exposition, I think this works. And when things need to be non-unital, I guess we will just wave our hands and yeah, we'll see. So the invariant is a complex unit of algebra. So A is A. So we define spectrum of A as the set of complex numbers such as lambda minus A. So this element is not invariant. Okay. So that's set called spectrum. Is literally. So what's the important thing here? Well, let me give a couple of examples. So in case A is continuous functions over a compact space, and F is an element in A, then what is the spectrum? The spectrum of F is just the image of this function. Because for every element in the image, when we subtract it, the thing will not become invertible because the function will have a zero. So it's the range of the function. And the other important example is if we take matrices, we take relate here. Well, the spectrum of A is just a set of lambdas, such that lambda minus this matrix is not invertible, so it has a kernel. So it's a set of eigenvalues of the matrix. So the spectrum is really a substitute for the eigenvalues of the L. And now we look at the largest eigenvalue, and that's called the spectral radius in modulus, which in principle, in this level of generality, the spectrum could be empty, but we will see that for math algebras, it's not empty. Well, we won't say it. I would say it, but we won't say it. So the spectral radius of A is given by rho typically, and that's the sort those lambdas that belong to here. And in general is minus infinity if C will be empty, but that's not super important for us. Okay, so let me prove a couple of things. How are we doing? Yeah, I think we're fine. So there's a proposition that we will be using, and that motivates some of the things that will happen later. Is that if A is a Banach algebra, always over the complex numbers, algebra, then here, so if the norm of A happens to be less than some real number lambda, then this implies that lambda minus A is invertible. And in fact, one can estimate the norm of the inverse. This is less than or equal to 1 over. And this says as a corollary, I won't prove this. I mean, it's not hard to prove, but in the interest of time, let me give a corollary for that. So the corollary is that the spectral radius of A is always less than or equal to the norm of A for a Banach algebra in this context. And that's because, so if so if lambda is in the spectrum of A, then lambda minus A is not invertible. Non-invertible, and therefore lambda has to be less than or equal to norm, right? Because otherwise it would be invertible, and therefore the largest possible value satisfies that satisfies this thing, right? So the main thing, and another so corollary this fact will appear later on. Is the following. Is that again with the same assumption? So we assume a Banach algebra. Well, let me first say notation that this will appear at places that I denote by A minus 1 set of invertible elements. So that's a set. And the corollary again of this proposition, so in the setting of Banach algebras, is that the set of invertible elements is open. And the map that assigns A to A inverse when A is invertible. So it's homomorph of course that doesn't only makes sense when A is invertible. Okay. So how do we prove this? So we take an invertible element, and we just have to show that there's a pole around this A, which is included in the invertible elements, and that's what we do. So this A is non-zero, of course, because it's invertible, so the norm is non-zero, and we take the pole centered in A with radius 1 over A inverse is included here, and that will prove it. So we take an element in this pole, and now we have to prove that this B is invertible, and to do so, we have the following. This is one of these we can take this difference, and this is now, because it's invertible, we can do this. This difference here, and now this is less or equal to, because the norm is somewhat multiplicative, the norm of A inverse times the norm of A minus B. Now B is close to A within 1 over the norm of inverse, the norm of 1 over A inverse. So this is less than or equal to 1 because of because of what we chose, right? So A inverse B is 1 minus 1 minus A inverse B. So by the proposition, this thing is less than, has norm less than 1. So 1 minus this thing is invariable. That's by the proposition. So A inverse B is invertible, and A is invertible, of course, so B is invertible. And well, the last part is also proof, but just wanted to emphasize this first bit. So the set of inverse of invertible elements is open, and this will come into play also later. So we come now to some important result on how to compute the spectral radius. So far, it's just this number, and it's defined like this, and it's less than or equal to the norm. But in general, how to approach the computation, well, it's not so easy unless you have some additional results, and that's a theorem that just quote. So this goes back to Irving and Geltner, and I don't know the year, but that's probably one should check, but that's probably in the 40s somewhere. So that's old stuff. So we'll take algebra. So if we take A name, and then quantum of A is the magnitude, and the spectral radius, and we can fill it by the limit of powers of A, and we can fill it like this. So the important thing of the non-empty part, this will appear. So you have two uses of these things now as corollaries. So the first one is already a result. I think this goes back to Mazur, which says that if it's a G algebra, which is also a division ring. So what is a division ring for maybe general public? So that's like a non-commutative field. So a field which is not necessarily a commutative. So every non-zero element can be inverted. Then, as we don't have to worry that much. So if we have that, then A actually the complex numbers. So it's the commutative and the complex numbers. So the only Banach algebra which is a division ring is this one. And the proof of this is simple once we have the theorem. So if A is name, say what? I guess any A. We take an element in the spectrum, maybe I should take, yeah. Then lambda 1 minus a is not invariant by definition, right? And I can take such an element because by previous result, this is non-empty. So you take a lambda here, then this thing is not invertible, but because it's a division ring, that cannot happen unless this element is 0. Okay, so that's what I'm saying is 0. So A is a complex number. So that's one part of the result, and the other part is that now when we have a system, it's easy to compute the spectrum in terms of the moment. The spectral radius. So, and then again, is a theorem, and this one we can prove because we have the theorem of Berling and Bell. So now we take let's take a system algebra, and then first the spectral radius of well, the standard is the non-algebraic squared, and if A is normal, normal meaning that means like it commutes with its adjoint. So A is yeah. So maybe I should put it like this. So that's what it means to be normal. So A star is the same as A star A. Then we have that the spectral radius is really actually equal to. So we saw before that it's always less than or equal to, but for normal elements in the system algebra, it's equal to. Okay. Right. So let me just sketch how we prove this part, the first part, by using Berling's result. Okay, so let's put B equal to A star A. Then it's note the following. B star, in fact, right? It's A star A star. That's a useful thing to know. So when you take an element and multiply it by its adjoint, either on the right or on the left, I mean in this order or the other. So when you take the adjoint of this is A star star. A star, which is A star star is A star. So we get what am I doing? Sorry, A star star. So it's A star first and then A star star. So there is A star A, which is again B. So B is self-adjoint, right? So now note that when we do B squared here, B squared is the norm of B times B, but B is self-adjoint, so I can substitute one B by B star, the other B by B. And now this by the system equation is B squared. So the norm of B squared is the norm of B squared. Okay. So that by induction then later, by inductive argument, but one gets that the norm of B add to the 2 to the k and power of 2 is the same of the norm of B to A for every. Okay. And so the norm of the spectral radius of B, which is the one we want to compute. So we want to compute the spectral radius of this guy, which is this thing. Spectral radius of base of A, which is the thing we want to compute, is the spectral radius of B, which is the limit of, we can compute this as the norm of B 2 to the K, these roots, I mean, right? I mean, for any n, we just take this subsequence and we can compute this limit like this. And because we know that this happens, this is just the normal by the equality we have there. And this is again the norm A star A, which is the norm again by the system equation of A squared, which is what we want. Okay. And the other part is similar. I won't go into this. And okay, let me see. Yeah, and a corollary of this is something that I was advertising before, is that if we have, so take two sister algebras and by a star homomorphism, so we have a star homomorphism between two sister algebras, then it's continuous with the norm of equal to 1. And we can prove this with what we do. But I will assume A and B unital. This makes my life easier, but it's true also in the non-unital case. So, but assuming with the unital and 5 equals 1. And now, so observe that because phi will send an invertible element to an invertible element. So since phi sends invertible elements, because phi is multiplicative and sends 1 to 1, this implies that if A is in that for every A in A, I guess, for every A in A, the spectrum of phi of A is included in the spectrum of, and that's by using this. So you take an element here, so the lambda minus this guy is not invertible, and that implies that lambda minus A cannot be invertible because otherwise the image would be invertible. So that's just by inclusion. And now this implies, so let me get this right. So the norm of phi of A squared, that's, so that's the norm of phi of A star A. Okay, so by the C star equation, maybe I can do this slowly. So that will be phi of A star of A. Okay, and because phi is, and it preserves the evolution and is multiplicative, this is the same as this. Okay, and this is, as we checked, this is exactly the spectral radius of this guy. Yeah, the spectral radius of A star A. And because the spectrum of this is contained in the spectrum of this is less than or equal to the spectral radius of A. star A, which again is the norm of A star A, which again is the norm of A squared. So this altogether gives that phi of A is less than or equal to. So the norm of phi of A is less than or equal to the norm of A, which tells us that phi is continuous with norm less than or equal to 1. So and since phi of 1 is 1, the norm is attained. So that's the other thing. Okay. And well, now, yeah, I think it's a right moment to stop because for break, because now I want to consider finite dimensional algebras and commutative algebras and some stuff about positive elements. So we can maybe take a break. Yeah, 10-minute break. I hope you didn't fall asleep. I mean, if you didn't, but I don't know. So I'll pause the recording for 10 minutes and then we'll continue. Okay, so resume with the second part of this first talk. Okay, about the general theory. So I will comment now a bit on the finite dimensional sister algebras. Okay, and well, we have seen that it's clear that it contains like this. Is always finite dimensional. And we will see, sort of see, I mean, I won't give full details, that these are the only ones up to isomorphism. So first is, well, say recall for those who know, and if not, that might be taken as a definition, that for any algebra A, the Jacobson radical is a set of elements with such that 1 minus AR is invertible, or in A, that's the same as all the element in A, such that 1 minus SA is invertible, or S in A. That's the same as the intersection of all maximal right ideals and the intersection of all maximal left ideals, and that's an ideal. I'm assuming we have a unit. So that's the Jacobson radical. Okay. And that's obviously in general free theory, but here we'll see it doesn't play. I mean, it plays a role for the theorem I want to quote, but not so much for the theory, because we have a Fermi lemma which says that once you start with A, the Jacobson radical is 0. That's a bit annoying. Well, so how do we prove this? Well, we take an element in the Jacobson radical. Now, if lambda is an element in the spectrum of this guy, then lambda minus A is not invertible. So lambda has to be 0 because otherwise, well, otherwise we will get a contradiction, right? So 0. then so, this implies that the spectrum is 0. So the norm of what we have to do is the norm of A star A. I mean, the spectral radius of this guy is 0, which is the norm of the spectrum. So A is 0. Okay, so the Jacobson radical is trivial. And now I can also, I mean, we use this also as an excuse to introduce the notion of idempotent unprojections. That this will appear later on. So that may be an algebra, it may not be, well, let's say a sister algebra, but it can be done more general, this definition. So an element in A is idempotent if its square equals to P and its projection if moreover its self-adjoint that's equal to its P star. Now observe that if we have a projection, P is a projection, then we have that of P squared, which is the norm of P star P. This is our equation, but because this P star is equal to P and P is idempotent, we get the norm of P. So either P is 0 or the norm of P is 1. That's kind of a silly observation, but we will use that sometime. Okay, so now we need another lemma, which says the following. So if we have an idempotent such that commutes with its adjoint, so it's a normal element, this time is P star P, then P is a projection. This guy is self-adjoint. So how do we prove this? Well, this is just, of course, if P is an idempotent, so P star is also an idempotent. Very easy to see, and we have the following, as we can gladly verify. If we multiply this out by using that this thing and just multiply this out, this gives you 0. Now this implies by the system equation that P is actually P star P. So P is self-adjoint. So that's an easy exercise. And now from here, I mean, with a bunch of other things which will be hiding under the rock, one can prove that if A is a finite dimension, algebra, A is isomorphic to a finite level of matrices. So, okay, and I will give a brief sketch of the proof, which is not the usual proof, I think. And this is given in Ken Goodrow's notes, which is a more algebraic approach, but still gives the result. So, a brief sketch of how this goes. So we know that A is finite dimensional that implies that A is an Artinian ring or Artinian algebra. Also, we know that the Jacobson radical is 0. So now you have an Artinian algebra with 0 Jacobson radical by the Artin-Benjamin theorem. That goes back to the 1890s, I think. That implies that A is isomorphic to product of this stuff, but has complex algebras. So that doesn't say that this isomorphism preserves the involution, that one has to check for that this is the case. And now to do this, well, now here we have central orthogonal idempotence. So let E1 EK be the central orthogonal idempotence such that the unit adds up to the sum of these guys and I times A, which is the same as I times A times EI because they are central, is also equal to M1I over C. So really this EI corresponds to the unit in MNI. That will correspond to this guy here. So since actually the eyes are central, we get by the lemma, so previous lemma implies that the EI are projections. Okay, so central means they commute with everybody, so in particular they commute with their adjoints, so they will be projections. And now we get that also EIA is a closed Stars of algebra of A. So it is enough to show that this guy, so EIA, is the same as MI as system or star algebras. Okay. So we reduce to checking this for each I. So we may assume that actually A is simple, so A is M by M matrices. So what we assume is so we have some generality. May just write it. Yeah, it's isomorphic to M as complex algebras, Mn of C as complex algebras, and we want to check that it is actually star homomorphism. Now, of course, by looking at the E11 projection here, so that's so we take F in A such that FAF gives us C times F, right? And the dimension of AF is F. So we take the idempotent F that corresponds to this guy, and because this guy satisfies these properties, we get the same for F. Okay. Now there's some trickery. That's really needs something. It needs to be done. We can replace, that's the part I'm hiding, by a projection. So we may assume this f is actually a projection that I still call f. Okay, so we may assume that. And now we let it by definition to be this thing AF, which is something that has dimension n because of this thing here. And it's a Hilbert space now. So if U and V belong to H, then it's that U is some guy that belongs to F, which is a complex number times F. So that's the inner product. So the complex number here is the inner product. So it defines Hilbert space. On this H. That's also some details that one has to check. And now the star homomorphism. Now, in A, there is not 5 sub A, H to H, which is just given by H here is multiplied by A, and that, so this is this line yields a star isomorphism from A to B of H. This H is kind of dimensional, so that's really. So that's a basic sketch of how one can do this. Of course, one has to check all the details. Huh? But as I say, if you check Goodrow's book on not so real and complex system algebras, the proof is there. Okay, so that's the basic thing. So we know that all the finite dimensional system algebras look like products of matrices, and also true. I mean, these two such things are isomorphic if and only if the sizes of the matrices agree, except for changes of order. So these are completely classified. And now we go to consider computer defined to us using systems. Give some details of how this goes. And the main idea is because of course we get a nice also result, and a very useful corollary that is will be used all the time later, which is a functional calculus. Okay, we start with a lemma, and as before, some things can be proved, but yeah, some others just take for granted. So let's take first a algebra with unit. Now, if M is a maximal ideal, then M is closed. And if, moreover, it is commutative, then the function is a complex numbers as well as algebras. Well, okay. How do we prove this? That's because we know things. So we know from before that the set of invariable elements is open. And clearly, because this M is maximal, this intersection is empty. Okay, so there's no invariable elements in the maximal ideal. So that implies, easy to check, that M is not dense. It's not dense in A. Okay. Because then you could approach any invariable element from elements from M and then put confirm this thing here. Because the invariable elements are open, right? So that implies also, that's easy to check, the closure of M is an ideal. So now you look at this, and since that is maximum, implies that M has to be closed. Okay. And now, well, what happens with the quotient? Well, it's not hard to see, but using this as an excuse to say what happens when we have a close to sided ideal and we take a quotient. So now we should assume that A is commutative, but we can first say something in general without proving anything, of course. Now, in general, if I is two-sided, close to ideal, A, then a quotient, just visual quotient, is a Banach with the following norm of class just the film of these quantities. Now, if A is a star algebra, then the quotient is also a star algebra with what one expects. So the star of the class is just starring the representative. And if it is a system algebra, the quotient is also system algebra with this norm. So that's the, I mean, we will be using this whenever it's necessary. Now, if going back to the lemma, so if now A is commutative and N is maximal, and maximal, then we know it's closed, and by these comments I made here, this quotient is a Banach algebra. And of course, it's commutative and a division ring. I mean, it's actually a field, right? So, Mazur's result implies that this is just input numbers times the unit of this thing. Okay. So it's the complex numbers as we were claiming there. So, okay. So now what we will prove is that all commutative algebras are continuous functions over a, I mean, in general, over a locally compact Howell space, but for convenience here, I will look only at the unital case and for some kind of arguments that we can write easily. So let me define this and then write a proposition. So that's a character. Very algebra, system algebra. Is a complex C opposite. So from say swimming to C. And so it's C linear and additive and multiplicative. So we denote by X3 the set of factors. Well, okay. So this set can be given. So this can be given what is called the double start topology. We start topology by which net of characters converges to F or lambda here if lambda of the converges to A for every A. So pointwise evaluation, they have to converge for every, I mean, in C. Okay. And okay, so what do we know? There's a expression that we use what we want to prove. So this is true in more generality, but let's just write things in terms of system algebras. So let's take a commutative system algebra, then, and we should say, yeah, then, first thing is that the norm of F is 1 for every character. Second part is that the space of characters is empty and it corresponds to the maximum ideals of the average. Max A or spend M. By this correspondence to you have a character, you associate its kernel. Okay. And finally, also get that where in A, the spectrum can be computed as the image of all the characters. Okay, so all these things can be, of course, checked, but okay, by using one really and the Van theorem, one sees that actually X A is compact. So, well, I mean, this thing is a compact space, and this space, which is the also called the spectrum of the algebra, can be used to determine this determines the algebra A completely. So for this, we need to define the Gaussian transform. And how to say this? So maybe I can just try this as a theorem of the element. That's also from the course. Okay, so we take the community system algebra, and then I want to write this. If A is in A, the map that goes from XA to C, and since this is just evaluation of its character to A, this is a continuous map. So we have this continuous function over this compact house of space. I was saying community, well, I mean, I'm assuming you. I mean, in the non-unital case, one gets continuous functions by managing at infinity or something else. But just to keep things more simple and filling time, I'm going to it like this. Okay. Now, we have this and this. The map still like hat that goes from to continuous functions on XA, it's actually to A like this. This is star isometric isomorphism, let's say. It's an isometer, and so well, it's continuous because of the topology we're given. So because we have this W star topology, this topology makes automatically these things continuous. So just a brief sketch of the proof. So A hat is continuous because of the topology we're given. So if a net converges here, then F lambda converges to F. So this implies that F lambda of A converges to F of A. That's by definition of the topology. So it's the topology that makes all these maps continuous. It's easy to check routine, verify that there is homomorphism. Now, one checks. So that's also a brief sketch of how things go. One checks that the spectrum of an element, that's by definition is also this is by the proposition. Here's proposition part 3. Okay, so part 3 here says that the spectrum of the element is the image of all the characters, and that's precisely A hat evaluated on all the continuous functions, because that means making F of A for every F. Right, so that's that. And from here, the spectral radius, which is remove of the values here, will be equal to the norm. This. So the norm we have, which is this thing here, is less than or equal to the norm. Okay. So one checks this is a morphism and also a star morphism. And now for the final part, let's check that it's isometry. So at least we see something. Here the norm that we have. The square this is the norm of a that square a hat, which is norm of a star a hat. And this is spectral radius of a star a, which we know is the norm of a square. So that implies this, which shows that it's isometric. Okay. And to obtain that the image is actually the whole of the continuous functions, one needs to apply the Sturm-Weierstrass theorem, which I won't go into, but that's how one concludes. So applying Strass theorem. We get that the image via this map is over all the character space. Okay. So this tells us how the commutative algebras look like. So they are all continuous functions over some compact space. Okay. The unit ones. And a very useful consequence of this is something that we will be using, I think, many times, and that will be the function calculus. So let's take system algebra in the community, and let's take A in A be normal. So recall that this means that A commutes with its adjoint. Then in this case, the system algebra is related by this element A. And well, if I want units around, so this is also true in a unital case. I will maybe comment on this. So if A is unital, then you take the system algebra generated by this A and the unit. So this is by definition, this is commutative. Now, we can take Z to be the inclusion of the spectrum of this guy inside the complex numbers. And then there exists a unique stuff of morphism. We call it here phi, from the continuous functions on the spectrum to A, such that maps this inclusion, this function, which is continuous here, to A. Okay. So phi is also an isometry. And the image of phi is precisely this algebra represented by a and 1 if we bring it around. Okay. So if a is not unit out, then we get this phi from the continuous functions that lies at infinity from the spectrum of a almost zero and sends the limit to a. So functions that vanish at 0 and send the included away. It's the same idea, but I can comment on this in the unit case. How does this go? So the idea is, of course, as I mentioned, well, first we have one can check that the spectrum of A, we can view it in A, or we can view it in this algebra here. Let's call it B. Okay, we can also view it in B, and it doesn't change. Now we know that now the map, that's basically how one constructs this phi. So the map that goes from the spectrum of B, so from the characters of B to the characters to the spectrum of A that evaluates its character in A is a homomorphism. Okay, so we use this equality here for that, and so this other map, because we continuous functions on the spectrum of A, built in A or in B, it's okay here to so the corresponding transpose map. So if you call this A hat, that will be A hat transpose. So that's an isomorphism. And now, how do we get to this phi here? So now, phi is simply, we go from the spectrum of A, so this is isomorphic to this one here, which is, as we know, by the Gelfand theorem, isomorphic to B, and B is itself A. So this is our phi. And one can check that this really maps the inclusion to this element A. So the thing is that we can identify A, that's the main point here, we can identify A as the inclusion from Z to the complex numbers. In case we had this spectrum include in the real numbers, which is what's going to matter later, or in the positive part, which is also going to matter right now, which we have time, I hope. That was the plan I wanted to do. So if we know that so A is normal and the spectrum is included here, right? So we can think of so I have all the continuous functions now. So the spectrum is somewhere here. And inclusion in the complex numbers is just looking at these continuous functions. So A actually corresponds to this guy, right? And now we can compute functions here, all sort of. So this is continuous functions over here is thought of as algebra of A, right? Via this phi, and A corresponds in this way to this function, right? And now you can do all sorts of functions here, and this will give you elements here, right? Like square roots and other continuous functions. Always continuous, they have to be continuous, but as long as things are continuous, you can map things from one side to the other. And that's super useful, and we're going to use this in the future. Okay, so in the last 5 minutes, I want to talk a bit about positive elements, and that will be it, I think. So, which is one of the crucial notions in system algebra theory. So, in C, one can think what is a positive element. So if you take any complex, well, any complex number will give you that the element times its adjoint gives you the modulus of C. Yeah, but it's always positive. And that's a way of saying what sort of thing you would like to be positive. Also, in C of x for a complex space X, you will get a function if f of x is positive for x, then one can write, one has to see this, one can write f plus g times g1. And in both these situations, when you have something positive in this sense, so in this case, we get, for example, that the spectrum of f. So this f is self-adjoint, so f is self-adjoint, and we also get that the spectrum of f, which is really much is the image for the whole space, this is included in the positive rings, right? So we want to generalize these two things that happen, and that brings us to the definition of a positive element. So, okay, so let's read the definition. A positive element is an element A in A such that A equals to adjoint. So that's the same as saying A is self-adjoint. So I will write this by this set as A is self-adjoint, and the spectrum into the positive reals. So let us observe that if A is self-adjoint, then of course A is normal, and we can apply the functional calculus before. So if we let of 1 of t to be this function, it's 0, and then the identity here, and then 2 of t, where this function, this one here, then by functional calculus, to this algebra by A and 1, and units around for to make things easier. So we get that A is actually, well, we get that if we let A plus, by definition, of 1 of A. So what does this mean? So f1 of t is a continuous function on the spectrum of this guy, which is included in the real numbers, because the element is self-adjoint, and we get, so we can take this map and map it to an element in the sister algebra, which by definition is called A plus. And if A minus is to t, then A is precisely A plus minus A minus, and A plus times A minus is 0. And also A plus and A minus are positive. Okay, these are positive because the corresponding functions are positive. They are orthogonal because the corresponding functions are orthogonal, and they add to the identity. They add to A because the corresponding functions, when you do this one minus this one, gives you the identity. Okay, the identity function. So this implies that every self-adjoint element is a difference between of two positive elements. So positive elements abound. Also, every element is a combination of two self-adjoint elements. It's over time, but I will be finishing soon. So, since also A is, it's like this follows the idea of like expressing every matrix into an admission matrix and an anti-admission matrix, something like this. We get that every element is a combination linear combination of four positive elements. So positive elements about, there are many of them. And we will use this constantly. I'll just write a theorem, I won't forget. So parts here, some parts are due to Polanski. So this goes back many years ago. So let us first, maybe I should have said that. So we denote by A plus is a set of positive elements, and also we write like this to mean A is positive. Okay. So the theorem says this, the following equivalent, and we'll finish with this result. So A is positive. So one part is that A is y1 star for some y. So this is what was proved by Kaplanski, I believe. The third part is that there exists a unique one, such that A is y squared, and this y we write y to be the square root of A, And the fourth part is that A is self-adjoint. And 2 times 1 minus A is less than or equal to T for some or for all T in with arrow to the way. So the parts that we will use most will be like every positive element has this form, and that you can also always take square roots, which is somehow in view of the functional calculus, this is not a surprise, because if you think your positive element looks like this, then of course you can take the square root of it. Right? You can take the square root of this function, and that will correspond to this guy that you have, to this y. And like this, we can have many other continuous functions, and some of them are actually very useful. Okay, so I believe that's about all. Yeah, sorry for the overtime. So next day, I will wrap up a little bit of what's left of the general theory and start with comparison of projections and positive elements.